problem. B5, right? So this right here is the nitric oxide problem. And so, as part of this problem, you just have to draw and fill in the electrons for a variety of different oxidation states of nitric oxide. And so if we were to go through and do that here, right? So nitrogen, right, has 5 electrons. So 1, 2, 3, 4, 5. And so, some people may have been freaked out because I stacked the two P's on top of each other rather than having them all to the side. That had more to do with the fact that I wanted to give space, right? So, but you can see where like the starting point is of all of the arrows, that they're all at the same energy, right? They're not different. But we have the nitrogens here, right? So that it has 5 electrons. The oxygen has 6 electrons. So 1, 2, 3, 4, 5, 6 in that case. So you have, that many electrons there. And so if we go through, right, and assign, the different types of molecular orbitals, this one down here, right, should be a sigma. This should become a sigma antibonding. These two right here should be your pi. This should be your sigma sigma bonding between the two 2p's. This should become your pi antibonding. And then this should become your sigma antibonding in those instances. And again, right, it has to do with the fact that, things play itself out that way because you have one of the atoms involved in this heteronuclear diatomic molecule, right, is nitrogen or lower. And so that's where you end up with that pi flip that you don't have, if it was, dioxygen or even, difluorine or even oxygen and fluorine, right, you wouldn't have that interaction. Right, and so we have those labeled, and now we just need to put in the electrons, and so we have 5 plus 6, so there's a total of 11 electrons that we have in this instance. And so what we want to do now is just simply fill them in using the Aufbau principle and Hund's rule and the Pauli exclusion principle. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So looking at this right here, we have one unpaired electron in the pi antibonding orbital between the nitrogen and the oxygen. And so now if we go to NO+, right, the difference here is that now we have one less electron overall, right? And so, the orbital ordering is pretty much the same, right? So it's going to still be sigma antibonding, pi, sigma, pi antibonding, sigma antibonding, because again, right, one of them is a nitrogen, the other one is an oxygen. And because there's a nitrogen involved, right, you have that flip of the pi and the sigma. And so we go now and we put in the number of electrons, right? One thing we have to pay attention to is that we're going to have one less electron. And so when I'm going to fill these in with that one less electron, I'm going to take an electron away from the nitrogen. But it ultimately doesn't matter, right? Because when you fill in the MOs, those are all going to kind of just like wash itself out in those cases, right? So we only have 4 here on the nitrogen. So 1, 2, 3, 4. On the oxygen, we have 6. 1, 2, 3, 4, 5, 6. In that case, so there's 10 electrons in total. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so there's 10 electrons here. Now, right, there's no unpaired electron in the pi antibonding orbital. It's just simply, ends in the sigma bonding orbital in this case right here, which, is a pretty important detail, right? Because when you put that electron into the antibonding orbital of the pi, pi antibonding orbital, sorry, what you're doing then at that point is you're starting to decrease the bond order in that case, right? So the bond order of NO dot, right? So NO radical is 2.5, whereas in the case of NO plus, right, it's 3, right? Because it has, 6 electrons in the sigma and the pi's, right? The 2 sigma star and the sigma at the bottom, right? Those cancel each other out. Whereas, once you start now putting any more electrons into that system, you start putting them into antibonding orbitals, and that starts making things less stable, so to say. Right. And so, if we go to NO minus, it's going to be the same thing, right? So we can just fill in, the MO diagram, right, with all the labels for everything the way that we had. But now, right, we have one more electron than NO, right? So now we're going to have 5 on the nitrogen. 1, 2, 3, 4, 5. And then on the oxygen, right, we're going to have 7, right? Because we're putting one more electron in. I'm just going to put that on the oxygen. So we have 1, 2, 3, 4, 5, 6, 7. So we have 7 plus 5. So that's 12 electrons that we have. And so now if we fill in the electron, the MOs, using the Pauli exclusion principle and so forth, right, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And so an important thing to note, right, for NO minus, because the two pi antibonding orbitals are degenerate, right, they're at the exact same energy, you don't completely fill one pi orbital, right, and leave pi antibonding orbital, right, and leave the other one empty, right? You have to put one into each one. And so, right, it's paramagnetic. It has two unpaired electrons in this case, that, kind of organize themselves in that way, right? But then, this kind of shows what's going on here. And so then the, important thing too is if we think about the bond order, you now have, a total of 8 electrons in bonding orbitals. You have 4 in anti-bonding orbitals. So the overall bond order is equal to 2. And, if you were to draw out the, the Lewis structure, right, it would show you that's the case, as well, right? That you would expect it to be a double bond, versus a triple bond like you would have for NO plus, or, a weird scenario like you have for NO dot, in those cases. So, but, for B, right, it says, now that we've done the MOs, there's some questions that we can answer about them. So for B, right, it says which oxidations are paramagnetic, right? And so anything that has unpaired electrons is going to be paramagnetic. And so NO dot, right, because it has one unpaired electron, is going to be paramagnetic. And then NO minus, right, because it has 2 unpaired electrons, is also going to be paramagnetic. So both of those are going to be paramagnetic in that case, not NO plus. What are the bond orders of the different oxidation states? So I already talked about that earlier, right? So for NO dot, right, it's 2.5. If you do that math, right, for NO minus, it's 2. And then for NO plus, right, it's equal to 3, because all you have to do is count up the number of bonding electrons, subtract out the number of anti-bonding electrons, and divide that by 2, right? And you get the bond orders in those cases. Next question is, which oxidation state do you expect to have the longest NO bond length, right? So we can just use the bond orders to tell us which one it's going to be. And so the one that has the lowest bond order is going to have the longest NO bond length. And so that's going to be NO minus. And then, the next question is, which oxidation state do you anticipate to be the most stable and why? So the most stable one that we would expect, right, would be the NO plus. And that has to do with the fact that, you don't have any unpaired electrons. You have, the highest bond order, so the shortest bond lengths between them. And so, those factors will, sorry, I'm just, contribute to the fact as to why NO plus is stable, right? And so NO plus, right, so NO gas is, right, a gas, but it's pretty unstable. Like, it's a super reactive because it has that unpaired electron. Same thing with NO minus. It, it wants to neutralize those anti-bonding things. Whereas in the case of NO plus, right, you can buy that as a salt. Right. I mean, you can still do reactions and stuff like that with it, but, it's, a lot of the reactions with NO plus don't actually really have much to do with the electrons per se, right? It has more to do that it becomes, a really good oxidant, right? Where it can, convert something, take away electrons from something else, right? Because it has a positive charge in those cases. But out of the, those 3 oxidation states, NO plus is the most stable in this case.